We're going to look at how we can set up integrals to find the volume of this spherical cap, which is defined by the chopping off the top part of a sphere of radius 2 by a plane that's 1 unit from the center. So there's the picture of what that little spherical cap looks like. And we're going to express the volume using 3 different coordinate systems just to compare. So let's start with Cartesian coordinates. So go ahead and put this on pause. I'm going to flip to a new board. See if you can set up the triple integral for this volume. Okay, so volume will be the triple integral over my region D with my integrand just being 1. You can decide which ordering you'd like to use when setting up your limits of integration, and I'm going to pick the ordering where I look at the shadow on the xy plane. So that means my 2 outside integrals are going to be with respect to y and x. So you can picture that shadow is just going to be a circle. And we just need to figure out what the radius of that circle is. So notice for this particular shape, the shadow is going to be caused by where the plane intersects the sphere. So the equation of the sphere of radius 2 is just x squared plus y squared plus z squared is 4. And then my plane is just z is equal to 1. And where those two intersect, I can just plug in 1 for z in the equation of the sphere. And I end up with a circle of radius square root 3. Okay, so now I can use that to get my limits. You can see I've drawn a ray here on my region R that goes parallel to the y-axis, and I want to see where that ray enters and exits my region. It enters along the bottom of the circle, exits up here along the top, so that's going to give me my lower and upper y limits. And then for the x limits, I'm just going to look at the smallest and largest values of x on the region R. And that's just going to be negative root 3 to positive root 3. And then for the inside z limits, I'm going to go back to my 3D drawing. I'm going to shoot a ray that goes along the z-axis, and I'm going to look at where it enters D, which will be down here along the plane, z equals 1, and look where it exits, which will be up here along the sphere. So I need to write those in terms of, in terms of z equals something in terms of x and y. So here I'd have z as 1, and then I'm going to solve for the top half of the sphere. I would get z as the positive square root of 4 minus x squared minus y squared. And as you know, once we get the limits, we take away the z equals or the y equals and the x equals that I was using as kind of guides. So that's Cartesian coordinates, and notice if we tried to start to integrate this, it's quickly going to become a pretty messy integral. So a better coordinate system is going to be cylindrical coordinates. So I want you to put this on pause, and we'll start a new board and try to set up the triple integral for the volume using cylindrical coordinates. Okay, so the first thing we need to do switching coordinate systems is my integrand now needs to include the Jacobian, which is just going to be r, which we showed in class. And then I'm going to just use the ordering dz, dr, d theta, since we've easily already found the shadow of this region on the xy plane. And now to do the outside limits, we're just going to rewrite the circular region R in terms of r and theta. So this is pretty quick. We just shoot a ray out from the origin and see where it starts, which is at 0, and where it exits, which is going to be at root 3. And those are going to be our r limits. And then we can see theta's got to go all the way around the circle, so from 0 to 2 pi. And as a reminder, theta is just this angle from the positive x-axis right here. Okay, now to get the inside limits, we're going to just do the same thing we did the previous page, because z is the same as in Cartesian. The only difference is we need to solve for z in terms of r and theta now. Okay, so we still have it entering along z is equal to 1, so our lower limit will still be z is 1. But now we need to figure out the upper limit, which is the sphere, in terms of r and theta. But notice, if we switch, so this is in Cartesian, if we switch this to cylindrical, x squared plus y squared is just r squared. So if we want just the top half of the sphere, we'll solve this for z, and we'll get just the positive square root, and that'll be up here for our upper limit. Positive square root of 4 minus r squared. Okay, so that's the setup in cylindrical, and notice the inside integral is easy with respect to z, and then once you need to integrate with respect to r, you'll be able to use a u substitution because of the Jacobian that's out there for you. So this becomes a pretty quick integral to do. But let's try one more setup. Let's try to also set this up in spherical coordinates. So go ahead and put this on pause and I'll get a new board. Now in spherical coordinates, we also need the Jacobian, which in spherical coordinates is rho squared sine of phi, which we showed in class. And then I'm going to use the ordering d rho, d phi, d theta. What will be helpful in these problems is to rewrite any boundaries of our region in terms of spherical coordinates. So let's rewrite the sphere in terms of spherical coordinates. Well, x squared plus y squared plus z squared, that is just rho squared. That's how we define it. So I have that rho squared is 4, or that rho is equal to 2. So remember, rho can never be negative. So that's going to be the equation of the sphere up here. And then let's get the equation of the plane down below. I forgot to leave limits for my integrals, so let's move this down so we have some, or I forgot to leave room for the limits of my integrals. So we move this down, we have rho is 2, and then I have z is equal to 1 for my plane. In spherical coordinate, z, we showed in class, is rho cosine phi. Okay, and as a reminder, phi is the angle from the positive z-axis. So this bottom plane can be rewritten. We can solve this for rho. This is going to give me rho is 1 over cosine of phi, or the secant of phi. So that's going to be this bottom plane. Okay, so now let's figure out the rho limits. So I'm going to start at the origin and now shoot a ray out from the origin. And I'm going to look again where this ray enters my region. So it's entering here along the plane, and it's exiting up here along the sphere. So that means that rho is going to start out at secant phi, that's along the plane. Secant phi will be my lower limit. My upper limit will be that rho goes to 2. Okay, now phi is this angle in here from the positive z-axis. So when phi is 0, we're going to be pointing right along the z-axis. This is where phi is 0. So we can see that we start with this region. We start when phi is 0. And then the largest phi is going to happen right out here. That's going to be the largest phi angle in this region. So we need to figure out where that occurs. That occurs at the intersection of the two surfaces. I.e., I'm going to have rho has to be 2, and I have that rho has to equal secant phi. So that tells me that cosine of phi has to be 1/2, or that phi has to be pi over 3 at the intersection point. So that's going to be the largest phi over this region. And then to trace out the full 3D region that we have, we're going to swing this all the way around in the theta direction, a full rotation from 0 to 2 pi. And recall, theta is the same theta we were using in cylindrical coordinates. So we also saw in cylindrical coordinates that from the shadow, the xy plane, that theta has to go from 0 to 2 pi. So these will be the limits if we set this up in spherical coordinates. And just a reminder for those of you who are not visualizing, theta is the same theta we were dealing with down here in the xy plane. Okay, so you can pick which of the 3 representations you'd like to actually evaluate. But when you do it, I'll leave that for an exercise for you. But when you do it, you should get that the volume is equal to 5 pi over 3. And that's it.